excited to be here. Did this a couple of days ago in Joburg, but I'm in Cape Town, so much the better. The first version of this talk I did actually back in 2019 when there was a new decade coming. It didn't include anything like a pandemic, but obviously it's been changed and things are moving. So I'm still looking forward from 10 years from now. If you haven't run across me before, as Robert said, I make a lot of podcasts, and the first of those is, of course, .NET Rocks. Any .NET Rocks listeners in the room? Oh, yeah, huge ones right there. So my friend Carl Franklin started .NET Rocks back in 2002. That's where the word podcast existed. So that's why we call it an internet audio talk show. Clever enough to come up with a word like podcast. Published every week, talking to some luminary in the .NET space. It's really a show for .NET developers, so if you're working in the space, we probably have something for you there. And then in 2007, I started a show called Run Ant Radio, which was aimed at IT pros. And so I've done that every week since then. There are about 900 of those now. And for a brief interval, we weren't sure if .NET Rocks, we made a show called The Tablet Show, where we talked about mobile and tablet development, and that goes back to the .NET Rocks eventually. So I'm speculating over the next 10 years of what software development is going to look like, and I'm quoting, Bill says we always overestimate the change that will occur in the next 2 years and underestimate the change will occur in the next 10 years. That is not a Bill Gates quote. He just said it, but he was actually quoting a guy named Ray Amara, who was one of the original computer scientists from Stanford back in the day. But the statement is good. You know, often we see a new technology, we think it's going to change everything immediately, and then it doesn't, so we're a bit disappointed. But sometime later, typically the decade horizon, it does come true. That's certainly true of the cloud. You know, we were talking about the cloud in 2008, and then it didn't seem that big of a deal, but now it's 2025, and you can't ignore the cloud. It's everywhere. It's just part of what we do now. There's more and more just greenfield into the cloud versus migrating our existing stuff up to it. So the cloud has certainly done its job. It's become a large thing. You can't argue that the mobile device isn't the primary compute device for most of the world. It's about 4 billion of these in operation on any given day. That's pretty much one for every adult human on the planet. So we are all now cyborgs. We have electronic extensions to ourselves, right? Now, of course, when you think science fiction cyborg, you think about it on the inside, but first it's kind of like you. And second, impairs upgrades. You wouldn't want to slow that down, so we keep it on the outside. But looking at most people's reaction when they misplace their phone lets you know it is really an extension of yourself. And we now have more access to more data than any other humans any other time. And I say data, not information, because I don't know if you've been on the internet lately. It's a bit questionable. So we've got a lot of data. Some people even call it big data. The phones are constantly making it, the cloud is constantly storing it, and these numbers just keep going up. None of this is particularly exciting or predictive. What do you think was going to happen? Of course, more compute, more storage, more data. What's actually going to change in the next 10 years that's going to affect us as software developers? And often I have to go and look at the hardware first, because in the end, what we do is reflected in the hardware we use. And I would argue the most important thing that's going to happen in the next 10 years is that Moore's Law is going to end. Now, Gordon Moore did not say what people think Gordon Moore said. In the 1960s, Gordon Moore had been a part of a group of folks that formed a company called Intel, and their first product was digital RAM. So instead of using core storage, other mechanisms of storing bits, they were starting to store bits in silicon, and he wanted to scale it up. And what he had observed was that roughly every 18 to 24 months, if his team worked really hard, they could double the number of transistors on a given piece of silicon for about the same amount of money. It was an observation. Somebody else called it a law. It is not a law. Laws are things that happen whether you want them to or not. Gravity, pretty hard to avoid. Speed of light, that's a tough one. Moore's Law only happens because a group of people try to make it happen over and over and over. And our industry has been built on the back of that. It did eventually apply to CPUs, which Intel helped lead the fight on. It is slowing down. Moore's Law is ending. The reason is pretty simple. We have now densified transistors to the point where it's almost impossible to make them smaller. And we followed this quite successfully. The first CPU starts in 1970, and you can go through today, this is an exponential graph of the number of of transistors on a CPU, that line's pretty tiny. But it's only because I have an exponential number on the left side here to keep it going up fast. And the issue is this. We're finally making transistors small enough that we're running out of atoms. So we start to look down in the substrate, looking at individual structures. These are arrays of transistors. And if you get into electron tunneling, you get to the point where each of those yellow bumps is actually a silicon atom. The blue hole is the boron atom. And that's what dopes the silicon to allow it to be a semiconductor. When you apply a voltage to it, it allows it to conduct, which creates your transistor effect. And when you're talking about a 3-nanometer process, well, silicon atom is 111 picometers across, or about 0.1 nanometers. So that's about 30 atoms. And in the crystalline structure, the boron only shows up every 4th time. So you're down to a handful. And now quantum tunneling effects start to apply. And silicon and crystal structures are not perfect. You can't beat the Planck length. You can't get down too small with just running out of atoms. Now, we're getting clever about it. We're changing up the structures on the atoms. So we're going to be able to play with this for a little bit while longer. But in the meantime, we can't expect more compute to show up every 2 years. Now, I've been doing this long enough that I remember a time where we literally built code for the silicon we were going to get 2 years from now. So we didn't mind that our software was slow because the hardware would fix it for us soon enough. That hasn't been true for a while. Well, it has been true that I still build slow software, but the hardware hasn't been fixing it for me for a while either. But there's a downside to knowing you're going to have new silicon that fixes problems for you all the time. You don't address the other things. And now other things are starting to be addressed. So an example of this is looking at the complexity of the 8080 architecture for CPUs. There are bits in here that are literally from the 1970s design-wise. And Intel has added to it year after year after year as it expanded the design. It has gone from 4 bits to 8 bits to 16 bits to 32 bits to 64 bits. And all that baggage is carried with us in the name of compatibility. But compare that to an ARM architecture where they started at 16 and then quickly moved to 64, it's simply a simpler architecture. Fewer cycles for the same processing capability. And today, if you look at things like the Qualcomm chip, it'll emulate the 86 instruction set faster than it can run. So we're hitting an inflection point where we're starting to shift other elements in hardware to continue the performance. And the great thing, if you're a contemporary software developer, is a lot of this we don't have to worry too much about because we're completely abstracted from. If you live in .NET land, you have a common language runtime, and that compiles on the chipset that du jour. You'll hit it in real time. So suddenly we have ARM, the Windows machines running ARM, and your .NET code will simply run because Microsoft did the work for you. It's ALR compiles to ARM chipsets. What do you think? Doesn't matter. And I would argue that, Apple still makes the most profound chip so far. The M4 is extraordinary. They've done the only logical thing they could do to continue bringing performance, which is to move pretty much the entire computer into the chip. This is not just the CPU, it's also the GPU and the NPU and a big chunk of the RAM as well. So same for the Snapdragon Elite, right? These are all concentrated. 12 cores on board, massive NPU on board. So we're getting extraordinary performance because keeping the wires just so responsive. So that's the hardware that's underlying it. And that's now starting to migrate in the cloud. Well, on the cloud, when you look at it at scale, what does it really mean to you? Less cost per transaction. It's the same reason we're running Linux instead of Windows in the cloud. It's about 25% discount. Well, we're distracted from the workload, you just run them. And now we're starting to have arrays of different chips available inside of the cloud to run them. So we've been insulated from this so far. But if we start to think about what's going to happen next, we have to understand that the hardware is going to shift on us, right? Now, language-wise, we've got lots of languages. And they tend to proliferate when change comes. So, Python's super friendly, pretty good in data science, challenges scale. If you really have challenges to scale, try JavaScript. Java, because you people hate yourself. It's not fair. Lots of people made a lot of money on that. C#, because Microsoft wasn't allowed to pay for Java anymore. And then, of course, C++ has the pain. Like some of these languages are from the 70s. Some of them are actually from the 80s. Nominally, C# only emerges about 2002, so it's one of the younger cousins in the space. But these are the old languages. You kind of look at more contemporary languages like Kotlin because Java people have too much pain, or Swift because Apple wants you to do something else. Or Go, which, I appreciate Go because this is a cloud-centric language. You have an infinite amount of compute and an infinite amount of storage space. You can build your language differently. You can solve the different classes of problems. It's a cloud-centric language. And Rust, because even C++ people need help. And, of course, TypeScript, because I need to be able to edit my JavaScript once in a while. Why did these languages emerge in the past decade or so? Because they solved the next iteration problem. They addressed the things that we were fighting with as we tried to scale, as we tried to maintain, as our software aged. Lots of these are easy to write from version 1, and then version 2 gets harder, and version 3 gets harder still. Now, with enough discipline, any of these languages can do the thing. You could still be writing in assembly. You could also hit yourself in the head with a hammer. Like, why? Why not use a tool that helps you go faster? Recidivist has been promoting Rust because it's a safer way to write really bare metal code close to the silicon. But we have such extreme processing time, most of the time we don't need to be that close to the silicon. And being abstracted gives us all this power. I just described it with new hardware, and you're like, oh, wow, how am I going to deal with that? Don't need to, because we're abstracted. If you were writing low level, you'd care about every chipset change. You don't want to. You shouldn't. It's not productive. The goal is to solve the customer problem, not to optimize to the processor. That's rarely the customer problem. Those are very rare now. Most of the time, we don't need to do that far away. And it's also why we see the web dominating most work-related software. Browser is the smart client, is the container. Why? Why has this one? Well, there's a bunch of good reasons. One is it's completely ubiquitous. Every device has it. The second is it's a security context that is safe and reliable. And deployment still sucks. And so the fact that we deploy through browsers makes our lives wildly easier. If you've been in the smart client business and have to deploy software the traditional way, even with the best tools out there, it's far more painful. And it's not the job. The job was actually to provide solutions to customers. And so when you have to fight with the plumbing to try and deliver results like that, it's just not worth it. And so we see the browser dominating for the foreseeable future. Now, the browser is undergoing an interesting shift. If we get into the AI part of this conversation, like the browser is the browser anymore, either. But the reason that shift is happening is because this is the context of most software today with no flexible endpoint. That doesn't mean we shouldn't still build small clients. We just have to acknowledge the fact that you have to justify that. The array of frameworks around web development also represent the issues with web development. Now, I've done this stuff now for 6-7 years, and I've seen periods where we've got a whole bunch of new JavaScript libraries trying to address the challenges of building quality software into browsers. We're in a lull again. We haven't changed a lot lately. I just want to acknowledge that every one of these tools is good. If you know the web, you can be successful with it. The reason there's so many is because there isn't one right way. And there probably never will be. And it would be dull if there was. Pick your tool, learn it well, you'll be successful with it. Now, we still battle problems around web development, right? We came up with this idea of a progressive web app, which, let's face it, there's a lot of cool features in the progressive web app back if you read it over. We only use one, right? We create a manifest to put an icon on a phone to fool a normal mortal and decide to pack for a second app. But that's a good feature that makes life easier and fine, right? There are other features that you want to get into it, but you'll rapidly find out that it's fairly challenging to do so. And web development is still twitching. We have our friend Steve Sanderson to thank for taking the WebAssembly specification seriously and finding a way to stuff C# inside of a browser and scared everybody, including Microsoft, who was so frightened of it, they kept it as an experimental product for years until Google shipped Golang as WebAssembly, so that Microsoft couldn't be accused of being the ones who threatened JavaScript. But the moment they did ship it, they released that being a product as what we know as Blazor. And some folks, this is the happy place for them. I get to write C# everywhere. Like the idea that we now have a context in the browser for whatever language you wish is very interesting. It isn't free. It's not simple to make stuff in WebAssembly, but it is possible, and it opens the door to a continuing diversifying space of software development. So I picked these pieces of the story of how we're going to build software over the next few years because they lend themselves to a broader thinking. That security context we call the browser today, even if it changes names, the idea of a deployed security context on every device that the customer is likely to use is a good idea. The fact that I can program whatever language I want is also a good idea. Likely to speak back to some kind of central resource, today we call it the cloud, makes sense. Those things aren't likely to change. So when I'm trying to figure out skills that matter to me, those are the ones I grab onto. Now, for better or worse, I make a show called .NET Rocks. So I should talk a little bit about .NET. .NET has gone through a remarkable revolution. It was originally built as an alternative to Java, even though Microsoft didn't want to say that at the time. They weren't allowed to play with Java anymore. They did make their own version briefly for a few years. So they built an alternative. It was built to build enterprise applications for Windows. And then sometime in the early 2010s, they realized they were a cloud company that didn't make any sense anymore, and they completely reinvented .NET to be a cross-platform open source product designed to run in the cloud. The extraordinary thing of that change is that you got to keep using the same tools the whole time. Normally, when we shift platforms, you have to reinvent the tooling on top of it. But somehow Visual Studio remains Visual Studio. There's a downside to that. It's confusing people. If you're still stuck back on 4.8, and I appreciate some people have a tough time leaving it because you made commitments to things that didn't make it to the new versions of .NET, it's still a productive place to work. And they're now on a cadence where they're shipping a new version of .NET every year. So last November it was .NET 9, and this November it'll be .NET 10, and wow, that's a lot of .NET. But it's stable. The feature set is complete. They're still trying to address issues. Like, I wouldn't worry too much about the framework. This is a great place to live and work. The client side is a more interesting problem. Back in .NET 6, they tried to consolidate the diversity of clients that exist in the Microsoft ecosystem. Starting down with Xamarin and Forms, which they had acquired, they built up to try and include all the Windows and alternative stacks on that. This is not a done or solved problem. And if you listen to .NET Rocks, you'll see me exploring around with things like Avalonia and OpenSilver. The fact that I see so many different smart client libraries out there speaks to this is an unsolved problem. And one of the issues here is that it's tough to justify the need for camp clients right now. When our devices are relatively stable, right? The phone has basically been the phone since 2007. It's been a slab of black glass the whole time. A tablet is an overgrown phone. There's only one kind that works good, and it's for those guys in Cupertino. And they take a walled garden that's not always fun to play. And as a software developer, the rest of the tablets are flexible with that. Windows on a tablet, okay. And then PCs, which the average consumer no longer has, but if you're working inside of an organization, you have control of devices, maybe you'll have a lot more PCs or to some degree laptops. The bigger problem here is we're still contending with the truth, which is, as software developers, we write code for a device that we don't run on. The code that runs on a different device than we write on. Building applications from your phone would not be fun. So we work from some form of PC, a laptop or a desktop, and then compile and execute to a different kind of device. Our dev loop has gotten much larger. If you've been doing this for a while, there was a brief period where the machine that you wrote the code on was what the machine ran on, and life was very good. It's also the exception, and it will never, ever happen again. Right? The heterogeneous client is the new normal, as much as we wish it wasn't. And so this battle to try and find one way to write once, run all, continues, because it's almost an unsolvable problem for a couple of reasons. The one being the customer does not care. They care that your app runs on their device. The rest of the devices can try. That doesn't matter. We care. We want one code base. We're trying to maintain it for all of them. And I've seen a bunch of solutions, and Maui is one of them, and they tend to have the same feel, which is that they're pretty good at iOS and Android, and questionable for everything. Pick your poison. None of them are easy. Learn it well. You'll get the best results you can. any certainty around this for the next decade? Absolutely not. The step that I expect, far larger disruptions to come than just trying to make it work for the phone. And I'd also bring up the Power Platform and all the other no-code, low-code solutions that are out there today. There's, again, more than a dozen at last count for me paying attention to these. I've seen this cycle before. What happens is the platform gets really stable. When it gets really stable, we build extremely simple tools for domain experts to do a niche of work. Forms over data really doesn't need a lot of code anymore. And that's what the no-code solutions are all about. They empower domain experts to do basic solutions. Most devs poo-poo these tools. I've seen that cycle before too. There once was a time when they all made fun of the C++ programmers made fun of the Visual Basic programmers. And for me as a Visual Basic programmer, I cried all the way to the bank. Because I made more software in less time. That's what these tools do. For certain classes of problems, they will crank solutions out. I'm not asking you to adopt them. I'm saying don't ignore them. They also need your help. Domain experts don't understand things like source control, security context, testing, reliability. They're probably going to need your help. Look, none of us are getting to the bottom of our to-do list anyway. So things that can be taken off our plate that are relatively mundane so that we can work on the that can help them makes everybody's life absolutely better. This isn't going away. This is an explosion for a reason. Because the cloud is stable, because the phone is stable, we are going to continue to have simplified solutions for certain working areas. That's a good thing. Until those platforms destabilize, and then there will be an explosion. I would briefly mention containers just because they're an ongoing thing. Depending on where you live in the ecosystems, containers are really present in mind or not. I would argue that the .NET world is the least containerist. If you live in Google Cloud land, everything's a container. It's really not optional. And most folks that live in Linux land, same thing. Containers are the way to go. We have more alternatives in the .NET space, but it's a robust technology. It is a simplification of virtualization. Again, we've gone through a few iterations on this, and there's more to come. If anything I can think that's happening into Windows is they're learning to containerize on the client because the software can play well with each other and promote. If you really study the way Windows works today, it's about line to application. It's like the application, you're the only one here, I'll give you anything you want. And then line to it so it feels like it's on its own because it does not work and play well with others. And that's going to continue. Again, for us as developers, it just means we need to be aware of what the security context is like. Before we get into really future stuff, I know that at this point I've raced through a lot of things and it can feel a bit overwhelming. Change is unnecessary. Our industry thrives on change, mostly because the companies that drive it make more money when things change. Not because that's a good idea. That's where the profit lies. But there's more than one way to have a career. The obvious one, the one that the industry promotes, is you jump on a new bitch and you run with it. I mean, the best thing about a 2-year-old staff is nobody has 5 years of experience in it. Even though a recruiter wants 5 years of experience in it, we're all kind of in an equal playing field. But I've also seen folks with really great careers grab onto a stack and be the expert in it, past its peak and into its long tail. Go look at how well paid a COBOL programmer is right now. They're all in their 60s and 70s, and there aren't making many more of them. And there's a whole bunch of companies that just can't seem to hang up that stack. And so they're doing very well. But I've also seen folks who jumped on ASP.NET Web Forms in 2005. And 20 years later, they're still maintaining a set of items. And looking at the end of the career saying, I need to move. My company values me. There's fewer and fewer of me. And these apps persist. We're probably not building a lot more of them, but they're there. They need work. And so that's a job. If that makes you happy. I'd only caution. The next thing about new things is you're constantly fed new information and you're used to changing all the time. The trap you get into when you stay on a stack is that you don't continue to learn. And suddenly it's like it looks like I have 20 years of experience in ASP.Web Forms. I actually have 1 year of experience. I've repeated 20 times. Learn new things. Press against the edges. Be aware of the platforms you're on. You want pain? Try to figure out how to make ASP.NET web forms work on a phone, right? There are ways to work around it. It's not fun, but it can be done. But I just want to emphasize the point. There is not one way to have a career here. There's a diversity of people in this room. There's a diversity and your pace in your work. There's many, many choices. So don't think you have to do it one way. Pick, explore, try things. There's a real power to jumping late. You know, the upside of not being the pioneers who didn't get the arrows in the back. You pick up something on second version and third version and move to it, there's a bunch of better materials around it. You want to have some fun? Try migrating the cloud today. The tools are way better. You want to move off a Visual Basic app from 99? There's actually still some really good tools for migrating that to .NET. They're wildly mature. That was tough to do in 2002. It is not that tough today. Okay, let's go to the more future stuff. Now, admittedly, AI is not that futuristic anymore. But this particular picture I used for a reason. It's important to get the context around this term. Artificial intelligence was coined in 1955 by a scientist, a guy named Marvin Minsky, who was trying to raise money from the U.S. military. So just to be clear, artificial intelligence, first and foremost, marketing term. It's for raising money. The first time the public heard that term was when Stanley Kubrick commissioned Arthur C. Clarke to write a script for a movie called 2001: A Space Odyssey. And in that story, and if you haven't seen the movie, please do. Admittedly, the first 28 minutes, there was no words, just music. It's a weird film. It's a Kubrick. There's a character in it. His name is Hal. Hal is an artificially intelligent computer that promptly tries to kill everybody, setting up our relationship with the term artificial intelligence. First, it was a marketing term, then it was a science fiction term for killing humans. Great thing to name software. All right. So, the other thing about artificial intelligence in general is that it is an umbrella term for a bunch of other things. Or as I like to say, artificial intelligence is what you call the technology when it doesn't work. Because when it does work, it gets a new name. Right? It becomes image recognition, or translators, or large language models. As long as someone's still calling it AI, it probably doesn't work. So you can judge accordingly, right? Now, again, this technology's been around for a long time. It's gone through a bunch of iterations. The image recognizers was the new explosion. That was the version of generative AI that really started in the early 2010s, along with the new vocal voice recognizers. You know, we had speech-to-text 30 years ago, but somewhere around 2012, 2013 with generative AI, suddenly you didn't need to train the model anymore. It just worked. You know, unless you're Australian, it didn't work for a second. And you can put this stuff in your code now. Right? There's all kinds of libraries. You want to do image recognition in your software? Feel free. Right? It'll work. I mean, be careful. But that emergence in 2010, 2011, if you think back to that time, scared a lot of people too. That was the time when you saw like Bill Gates and Elon Musk on the same side of the problem. They aren't anymore. I miss the old Elon. The guy who flew his first time space was kind of fun. This guy? But it was those guys who were concerned about Google. Because Google had most of the best brains in that space. And they created a group they called Google Brain. And so this group of tech billionaires decided, we need to put this into the open. I'm obsessed with their goals there. This is where OpenAI comes from, was the group of tech billionaires, including Elon and Reid Hoffman and Altman and all those guys, said, hey, we're going to fund an organization to do AI in the open. And really, it was a recruiting drive to pull the best scientists in the world into a single organization. So except for that part where they lied, it was a great idea. They didn't fund it sufficiently to do almost anything. Elon kept saying you put $100 million in OpenAI. Lie. Turned out it was about $16 million, which admittedly more than I can put in. But also like 10 Teslas, okay. But really, OpenAI kind of set it up to never succeed. It was underfunded. Wasn't really going anywhere, but they did make the transformer model. They were working on translation originally. They were trying to make a universal translator, tokenizing language into a common set of numbers that could shift to any other language. And as the model started to grow, it got interesting. And then Elon tried to take it over and got kicked out, which is why he's still grumpy about it. And then Kevin Scott showed up. So GPT-2, OpenAI was so broke they had to make different size models so they couldn't afford to run it themselves. Scott thought it was interesting, talked to Satya about it, and basically went to OpenAI and said, tell you what, we'll lend you $1 billion, but you have to move all your workloads over to Azure. Which really is what it's saying. We're going to lend you $1 billion, but you're going to have to pay it back to us. Which is a pretty good deal for Microsoft. But that set up GPT-3. And as soon as GPT-3 started to work, Microsoft get $2 billion and more. Now, GPT-3, if you ever played with the early version, and I don't think you have, it was not that good. Like, in terms of a language, conversational language tool, it was not awesome. And the OpenAI guys consider that the challenge here was not just do the core model, which was take sentences off the internet, hopefully good sentences, but there's plenty of times that they didn't take good sentences off, and train so that given the first half of the sentence in token form can answer the second half of the sentence in form. That was the original training model. And they had questionable results. So they did a second order training model, where they would take all those responses, and they gave them prompts, and then they would give them 4 responses, and you'd get a person to rank them. And so they paid people, typically in low-cost parts of the world, like Indonesia, to keep ranking these steps over again until they ran out of money again. In the fall of 2022, they were about out of cash again, and so they decided, let's go train in public. We'll just let regular people do this, and we'll take training sets from individuals. That's ChatGPT in November of 2022. And if you remember, if you played with it in those early days, it always got back 4 answers for every prompt you gave it. If it was right, it was actually meant to rank it. That's what it was for. The problem is that 100 million people signed up for it for those 2 months. I got a chance to talk to some of those guys and said, why even 100 million people signed up for this? Probably because we did it over Christmas and nobody wants to talk to those in-laws anyway. So they talked to software instead. Actually, Sam said to me, like, you're a dog. Why are you talking to software? Anyway, they signed up 100 million people, and that's a big deal, right? Then Microsoft's like, 100 million people is a lot of people. We should do something with this. It's also the first technology that Satya Nadella got to put his fingerprint on. Like everything else that Satya had done up to that point, he already started at Microsoft before he became CEO in 2014. But here, in 2023, he could take a thing. It was the first time he ever put out an internal letter inside of Microsoft. Famously, Microsoft Bill Gates would put out these letters. He'd like, he put out the internet tidal wave. It's like, we have to get on board the internet with everything, and the whole company pivoted towards internet. And he put out trustworthy computing, because all those terrible security features, And here was Satya for the first time ever in January 23, Paul Letter said, here are keys to OpenAI. All of you have to build something with this. Experiment against your product. So essentially train the tens of thousands of developers that exist inside of Microsoft to experiment with OpenAI. And that's where the Copilots come from. Way too many of them, but that's where it comes from. But of course, that name doesn't come from Microsoft. That name comes from GitHub. Because GitHub's actually based in San Francisco. They're closer to the OpenAI folks than Microsoft is. And so they grabbed one of the early versions of GPT-3 and started training it against the public GitHub set and got the first results that were usable in any way with GitHub Copilot. It's such a good name, so you know Microsoft didn't think of it. Because it keeps reminding you the truth, which is you're the pilot. It's your fault. Be careful. But the nice thing about GitHub Copilot is that we're used to criticizing other people's software, even software. And the compiler always gets a say, so it gave us a little more shape to work with. The fact that Microsoft ran with this and made Copilots everywhere is problematic. At one point, I think there was over 200 of them, at least internally. Now they're trying to dilute them down and try to concentrate the most valuable parts of it. But you can see the experiment happening out in the wild. It is an experiment. And just last week at Build, they talked a lot about these latest iterations of agentic AIs. The thing that I've learned over the years is when they keep producing new products over and over again, it's because the old product didn't work that well. Not that I don't see productivity gains from GitHub Copilot, without a doubt it does. Not that it's replacing any developers by any stretch of the imagination. But we're seeing 20-30% performance improvements, like more code checked in faster, generally at higher quality, less remediation, which speaks to the truth, which is, as a developer, it's hard to justify not using these tools, because they can make you more productive when you use them. The next iteration they talk about at Build freaks me out just a bit, because now you can tell Copilot to take on an issue for you. I would encourage you, if you like hanging out on GitHub to go look at some of the Microsoft projects where the Microsoft people are trying to use this, because now what's happening is they're signing an issue to Copilot, it's writing the code and submitting it as a pull request, and then you get to watch a human write back to the software about how bad their pull request is. And then there's another pull request, and it always agrees with you. You're right. My coding sucks. Here's a new version. And again, and again. But that's the point we're at now, is this idea of this sort of agentic model where it is not just taking a chunk of code that you've asked it to write, but it's looking over all the process and writing pieces of it. I haven't found good ways to declare one model better than the other. I constantly ask that question. There's a group of folks at Microsoft told me, hey, Claude 3.7 is the best. I'm like, how do you know? It's hard to measure these things. But they're worth paying attention to, and it's interesting to see how they integrate into the workflow. You know, as well as I know, there's a big chunk of code that we write every day. It's pretty boilerplate. That if it could be more automated so we could focus on the tougher bits, so much the better. But also it's good to remind ourselves, as software developers, their job was not to write code. It was to provide solutions to problems for our customers. That's why you don't write your own cryptography libraries anymore, right? That's a small problem. Well, we may now have a new tool for solving other classes of problems a little bit more dynamically. And as we're playing with the interface on it, again, quality is a problem, but it speaks to a time when you're going to be able to focus on the most important bits. The real issue here is that we're in a hype cycle. Right? And if you've not seen this graph, let's bring it up again. This happens over and over again in our industry, specifically in technology. We have a technology trigger event, like ChatGPT, like Netscape's IPO, like the iPhone. And then we go up this screaming crazy at the peak of inflated expectations, where it's going to do everything, and everything's different now, and it's all going to change. And then we go screaming back down to the trough of disillusionment. And that can get really destructive. Like, you can go too far down, get legislated against, and get, look at poor BitTorrent. Cast in the eye of Daxter. Not a bad protocol, kind of efficient. Look at blockchain. Not a bad protocol, but wrapped up in crypto scams. So there's a downside to this cycle. Sometimes decent technologies get stained. And I'm worried about AI going through the same cycle as they get overhyped. I think we're still coming down. We haven't hit the bottom of the trough of disillusionment. More dumb stuff has to happen before we start to climb out into what's realistic. Right? The dot-com boom and bust was this also, and yet the internet and the web persist. So while we're in this, that queasy feeling you have is correct. We're in a hype cycle. Stick to your engineering principles. Always ask this question: how do I test this? How do I know that it's good? They tell me the LLM's a great summarizer. If it wasn't, how would you know? Are you going to go summarize the document yourself and compare? I don't know that you will, actually. So therein lies the problem, right? Now, you can ride the hype for money if you want. Just remember, you're being a mercenary. Right? Don't believe your own hype. If you're going to be a responsible engineer about this, tread cautiously. Test. Balance it. It's not going away, but it's also not grown up. The next 10 years, this will be resolved somewhere. It looks like the crash is not going to be as spectacular this time. We're going to get through this. That being said, the whole AGI superintelligence thing, it's science fiction. I guarantee you Sam Altman in the next couple of years will declare AGI achieved. He's just lying because that's his business. He needs his companies to see. He will simply change the goalposts. When people tell me AGI is inevitable, my question is always, so when you say AGI, what do you mean? Right? What is an artificial generalized intelligence? In science fiction, we had the superintelligence, where this thing happened that has never happened in nature ever before, where enough stuff was put together that it got more organized by itself. Right? That's not how entropy works, but okay, it's good for a book. Don't think it's good for reality. So far, the stuff being spat up by LLMs isn't better learnings to make better LLMs. We're calling it AI slop for a reason. So we're not on a righteous cycle that actually improves the world. Right? We're still feeling around for what is possible. There are very good books on the space. They're extremely difficult to read because they get you into hard problems like what is consciousness? What is sentiency? And if you take your time with these books and really think about them, it won't take you very long to say, I'll tell you what it isn't. It isn't a large language model. Right? A large language model is a way to condense a large amount of data into a smaller space. It is basically the JPEG of data, a lofty storage technique. Treat accordingly. The more stuff you stuff into it, the fuzzier the picture actually is. You're already seeing this with a lot of the LLMs. They're starting to focus on narrow areas. Like we stumbled into this with GitHub Copilot by accident. That because code's a relatively narrow band, it works fairly well. When you completely generalize, it gets worse, not better. And now you're seeing good-looking LLMs working on smaller, refined data sets because they're more consistent, reliable, and testable. So we're going the other way. Generalization's not it. Not to say that we aren't doing good things with generative AI. This is the weird part. The good parts are mostly in healthcare, things like AlphaFold for doing protein folding. This has been completely open source. It's a way to understand biological processes in a way we've never done before, and it's profoundly important. It'll take a few years for us to see this in the rest of the world, but if we follow these things closely, good things are happening here. We've created 2 entirely new antibiotics from data analytics from generative AI. Good things are happening in space. We're starting to take translation for granted, and it just works between multiple languages. The original strategy that OpenAI had around the tokenization strategy, it's just become a thing. I'm talking to folks in the gaming industry that are talking about a whole new way to build out games, where the LLM is writing new scripts dynamically and interacting with you, so all of our gaming experiences will be kind of tailored and unique. And also cost-effective, because game development is extraordinarily expensive. And it gives us an idea that we might have a whole new way to approach UX. If I now have a device that can see you and react to your reactions on the interface, I can tailor the interface to you. It's an interesting way to think and explore going forward. This is early days, but if you really want to press the edges of what's possible, think about what you could do to build a UX responsive to the person based on their individual reaction. Starting to see space tailoring in that space. Okay. We should also talk briefly about what's going to happen to the phone. The phone's kind of been the same for almost 20 years. It's dull, right? Some of them have 2 cameras, some of them have 3 cameras. I don't know what cameras you only want, bigger, smaller. It's kind of the same. The goggles are out there. They're just not good enough yet. They're expensive, and they don't do enough. Now, smartphones used to be really expensive, too. I'm kidding. Smartphones are still really expensive. The goggles are even more expensive. The question is, can they bring anything to the table that makes a difference? And we've seen a few attempts. Apple's struggling. HoloLens is essentially on hold, although Microsoft stopped selling HoloLenses too to preserve their current inventory because they have a bunch of field applications out there. They're working in vertical industries. You have a $35, $100 headset and take $1,000 a month to rent. They are not consumer devices, but for certain verticals, they make a lot of sense. And so that reminds me of the BlackBerry phone back in the 90s, where you needed to run a custom version of Exchange. You need 2 guys in white lab coats to keep it alive. The phones were more than $1,000, and only executives had them, but you had email on your phone. Right? Big deal. It wasn't the iPhone that came 10 years later. So I think we're in the BlackBerry phase on augmented reality. Right? Getting all that stuff inside of an individual device is really, really hard. Meta's trying to make a consumer product, but you can't start with social media. That's the end game, not the start game. And so that hasn't gone all that well. But that's fine. You know, they've got some interesting headsets. And they now have this new version called Orion. This is like a concept car of a headset, about $25,000 a shot. But you can't buy one. Mark has to want to give you one. I don't know if you want to be friendly with Mark that way, but the experiments continue. And the idea of everything is a compute surface that we could work anywhere is interesting. It's just not mature yet. You can explore in this. There's not a lot of money going here right now because AI is home for better. All right. And then, of course, Snap's last version. Last little bit to wrap up with is quantum computing, because everybody asks. The thing to remember about quantum computers is they're not general-purpose computers. They're supercomputers. They're designed to work very specific categories of tasks. And about 10 years ago, we had a bunch of breakthroughs, starting with Sycamore from Google, and then which was using the transmon approach using liquid helium to create qubits, which is expensive and it's challenging way to operate. You don't want liquid helium in your life. It's dangerous. It explodes. It's only liquid in a very narrow temperature range. You have to pre-cool everything with liquid nitrogen first. So, I hope you've got a lot of doers around. But if you get it over temperature for any reason, it expands 150 times and it will blow rooms apart. So any room that deals with this stuff has big ventilators. Right? That's why these quantum labs are so specialized. You need to build a building around the computer. It reminds me of the old mechanical mainframes of the day, right? The Chinese took a totally different approach with their photon computer. They've got some interesting results on that. And IBM's made a whole series of processors. Like IBM now made one big quantum computer they call System 2. There's exactly one of them. It's in New York. And it's massive. Huge cryogenic cooling system and so forth. And every time they shut it off, it breaks. They have to repair it to cool it back down and run it again. And you may have just seen the announcements from Microsoft around the marijuana processor, which is really defines a new category of physics. They've only just announced this thing. They've made some hardware. We don't know how real it is. But the reality of these kinds of compute problems is not cryptography. Cryptography is the thing that the press understands when they talk about it. There's plenty of solutions to cryptography. We're just going to get off of prime keys. We have asymmetrical encryption and lattice encryption, which are already being encouraged. In fact, Microsoft is now deploying asymmetrical encryption into Windows 11 in the Insider program today. So bit by bit, we're just going to move away from the RSA approach to encryption, and one of that is going to feel like quantum is actually going to come true to some point of effect encryption. The far more important space in quantum computing is quantum chemistry. So my favorite example is the nitrogen example. If you are farming, 5,000 years ago, you knew you can't just plant wheat every year. You grow less and less wheat. You have to rotate the crop. And the reason is you're depleting things from the soil. And so now you plant beans, and then you plant goat grass, and you allow the soil to replenish itself. By World War I, we had figured out how to make fertilizer industrially because it also made explosives, yay war, which means you didn't need to do that anymore. And we kind of ignored the fact that beans put minerals back in the soil. And how do they do that? Well, we've been studying this for about 150 years, and it's a thing called nitrogen. So it's an enzyme that lives in a rhizome on the root of the plant. So when you harvest the bean pods off the part you eat, you plow the plant under, and these things would break down and literally refertilize the soil. But somehow, this little weird compound would take atoms of molybdenum and atoms of iron and combine to do a catalytic reaction to make fertilizers ammonia. And we don't know how that works. In fact, we can't figure it out with classical computers. It's too complicated. This is a quantum computing problem. It should be solvable with about a 200-qubit quantum computer in a couple of hours. And that would open a door to then building a process to do low-energy production of fertilizers. And currently, 1% of all the energy consumed on this planet is the production distribution of fertilizers. So you can cut that down. So I can imagine, even if it's an arid water, a little state beside your plant that's making the things your plant needs. That's one. Same for batteries. We essentially use alchemy to create batteries. We just try, what we've gotten is good at testing quickly, right? We don't actually know how to make better batteries. But if we could actually solve the battery problem in quantum computing, we could make it dramatically better. Huge jump forward. Same for superconductors. But all these problems are deterministic problems. Once they're solved, they're solved. How many quantum computers do you need? And that's the old Thomas Watson line when he was talking about selling the first mechanical mainframes. He thought there was maybe a market for 5 of them. He was wrong. There was 16. But they got better, right? When computers look like this, you only need so many of them. And you really can't picture, this quantum computer, what it would look like going forward. And it reminds me of the story of the first transistor. This is the Bell Labs transistor made of germanium. William Shockley was involved in it. And Shockley also went on to create a company called Fairchild Semiconductor, where he learned to make semiconductors. And in order to make the semiconductor, he used old mechanical computers to compute how to dope the silicon, that he needed boron in a certain ratio out of the silicon to make it a semiconductor. That made it possible to build the silicon substrates that make the model computers we use today. And it makes me wonder if we have to do the same thing for quantum computers. But these unreliable, unstable quantum computers will be the thing we need to make the reliable qubit, the same way Shockley used mechanical computers to make the reliable bit. You can't see the Apple M4 looking at this. But history sometimes lies. Maybe that's the pattern that's going there. But to wrap up, with all the speculation I've already done, you're asking what's next. Here's the one thing I know absolutely for sure. The way to know what's next is to make it. That's our job. We make decisions every day about the software we make, about the tools we work on, about how we approach things. We get to decide the future. I hope we decide well. Thanks for your time.